All right. This is Daniel Minizini, your inquisitive geologist at Mini Geology, a radio show, KPFT HD2 channel, here from the beautiful Montrose headquarters of KPFT Houston, talking with all of you geologists, geoscientists of the world and beyond, because we have also the astronauts that are in the International Space Station that are listening. And today we're going to talk about even beyond that. We're going to talk about Mars. In fact, we have in here today Kirsten Siebach, professor at Rice, at the Department of Earth, Environmental and Planetary Science. She is currently a member of the Science and Operations teams for the Mars Exploration Rovers and the Mars Science Laboratory. Welcome very, very much, Kirsten.
Happy to be here.
So, we are also excited when we talk about Mars. I don't know, I'm a sedimentologist like you, and stratigrapher, but studying some rocks here in the southwest Texas. Like when you say Eagle Ford, people, they don't really get so excited.
Yeah.
So why do you think that people are so excited when you talk about Mars?
Oh, it's always exciting to explore. It's exciting to see that there are other planetary bodies in our solar system that actually have rocks that are very familiar to us here on Earth. And when we look at those pictures of Mars, especially the kind of true color kind that Curiosity can send back, and we get to see deserts that look just like ours, minus a few plants here. We really get this sense that that we are exploring, and that there is so much more out in the universe, but also our planet has some similarities to what's going on other planets.
So when we talk about Mars, do you think that there is a narrative that people, they understand and is in the air, and as you said, is about exploration. But there are also many other places in the world, in this planet that we're exploring. Is it anybody trying to create a narrative to excite the people, the audience, about Mars? Or is just serendipity and nothing organized? It's just about the simple human curiosity about something that is so far away from here?
I think it's a lot of the simple human curiosity. I speak to a lot of groups. I've spoken to young students, and even young students just are immediately enthralled. And I think that it is a natural tendency to be excited to explore someplace that seems so alien and yet in some ways looks quite familiar.
So how many Martial geologists are on this planet?
So we have teams that work on each of the rover missions, and each of those teams will have a couple of hundred people from around the planet that work together to help operate the mission and work in the labs and make sure that our instruments are calibrated on Mars and that we can make decisions, because we're operating these robots every day on Mars, and so we need to make sure that we've got enough people working together to operate the mission and to try to publish the results and share what we're finding with the world.
Even if they are not necessarily geologists, there may be also engineers and...
Yes. Yeah, there's a variety of engineers, chemists, meteorologists, atmospheric scientists, all varieties of earth science, really, and then a variety of engineers who build instruments and rovers.
And what about geologists? Do you think we already have a critical mass about geologists? Because geology, as any other science, it advances very fast if they have an important critical mass. Do you think you have reached a critical mass in the discipline that you study?
I think with our last few missions, we've really been able to bring back more and more surface geology data and finally get scenes that really look familiar to Earth geologists. And as we've done that, and as we've really reached the point where we have enough data for typical Earth geology approaches, we've been undergoing a transition, especially over the past 5 or 10 years, where we've been pulling in more and more of the geology community and asking the experts that we have here on Earth in terrestrial geology to look at our Mars data and to help us understand. And so you've kind of branched from a group of mostly planetary scientists who look at whole bodies to kind of pulling in more and more of our terrestrial geology experts. And I'd say right now we're in that transition. And so we're bringing people in, we're sharing our information at conferences like AAPG as opposed to only lunar and planetary science conferences, and kind of getting a mix of opinions and trying to reach that critical mass. It's kind of unique for each mission. So we're moving towards that.
And you are following this transition. When did you enter this magical world of Mars geology? How many years ago?
I've been helping operate the surface missions for the last 10 years, just over 10 years now, starting with the Phoenix lander mission to Mars. And so it has been fun getting to watch that transition and being part of that transition as I went through school and graduate school and tried to seek different types of expertise on these questions.
So tell us more about this transition. Who was in charge and involved in the studies of Mars at the very beginning of your career, and who you are looking for now? Who are the geologists that the Mars community is looking for?
So at the beginning of even just about 10 years ago, we were, let's see, the Mars community was dominated by remote sensors, or people that could use spectroscopic data, especially orbital data, which we gathered from satellites that were orbiting Mars. And then folks who had worked on some of these previous missions starting in 2004 with the Mars Exploration Rovers driving around on the surface and starting to collect that surface data. And so we were kind of working with a team that was planetary scientists, some geologists, geochemists, who had worked with Mars data for a good amount of their careers, and they would do some Earth geology and talk to Earth geologists. I'd say now we really are branching out. So now the last couple of major missions, the Mars Science Laboratory, for a while the project scientist after landing was John Grotzinger, and he is certainly made his name in terrestrial geology, Precambrian studies. And then this next mission will be led by a geochemist, Ken Farley, the Mars 2020 mission. And so with those kind of leaders, we've pulled in a lot more people who have made most of their careers understanding and experiencing Earth geology, or people who have done a lot of field work and seen a lot of rocks on Earth. And so that's where we're turning more and more. We'll sometimes bring in experts to talk to our team from places like from oil companies or from just different terrestrial experiences, different aeolian sedimentologists. So it depends on what we're finding on Mars, obviously, to look for the experts in that field on Earth and have them think about the data in a slightly different way, because we have different data limitations when we're acquiring data on Mars. But we've been reaching out more and more to different parts of the terrestrial community and bringing people in.
I'd like to talk about the data as well, but before that, I would like to talk about the people. So you're a professor at the university. You're at Rice University here in Houston. Do you think that the students that they come and they enroll in your classes, they do it because they are fascinated by Mars? Would they like to become a Mars geologist?
Some of them certainly would. And I think that, and certainly, those classes will help them along the way. But I think that it also helps Earth geologists. I think that it helps us to think about problems in a different way. I think creative approaches are always beneficial and kind of make us think differently and have a different perspective about each of the rocks that we see, right? As you were going through school, seeing your first field trip and then going out to a different field trip and kind of understanding, oh, that's not always the way the rocks work. Let me go see this other basin and see this other basin. And as you kind of accumulate that information as a sedimentologist, you learn to appreciate all of the different ways that Earth has worked through time. You learn to appreciate all of the different ways that rivers could be flowing across the landscape, or that deltas could work, and all the different provenance rocks you could be collecting from and how that might affect what you're seeing. Now, when you look at Mars, you really do get a different case, right? You have to subtract the influence of life in almost all cases and try to understand what it would be like without life. And you have one rover traverse. And so you have to kind of think about, well, if I were there on my own, I could draw I could draw stratigraphic columns for a number of different places, but instead what I've got is one rover traverse. And so when I'm looking at this, how do I understand this in a way that reflects from my understanding of Earth? And so each of those little twists, and one of the other ones is that most of our sediment is basaltic. It's first order volcanic sediment. Even in the sedimentary basins, it's broken up basaltic rocks. And it's just each of those little twists that makes us think about it in a different way and think about how can I solve these problems more creatively? How can I answer the same questions as I've answered on Earth, but under these constraints? And I think thinking that way benefits all of us, right? I think taking that external perspective or that novel creative approach will help us in all of our work.
I like the fact also that you talk about this transition, because also in the industry there is a transition right now, and so when the students, they ask which kind of professional would you like to have once I'm out of university, so that's something that is changing also right now. Like years ago you had specialists, maybe around 10 years ago the industry started requesting generalists, going back to the generalists, one of those rounded geologists typical of the 60s. Mm-hmm. And now industry is asking to go beyond geology, and the students, they should know a little bit about the environment at large. So which country they're studying, what are the markets in that country, what is the geopolitical situation. And so I really like the fact that you are also explaining what the students, they should study right now to understand planetary science and in specific Mars, because things are changing, and when you studied, they request something different than you are requesting right now to your students. Is that right?
Yes, yeah, absolutely. Things are changing and becoming a lot more interdisciplinary, and especially with exploring Mars, a lot of teamwork skills and understanding the engineering side as well as the geology side, which I'm sure is similar in industry.
Correct.
Being able to pull together all of those different disciplines and ideas and kind of cultures, and then being able to communicate with each of them, which is really one of the key factors.
And but I said that I would like to touch on the data as well. Can you tell us something about the amount of data and the quality of data that you get from this new place, which is Mars? Because we had zero data not that long ago. And now, how is that growing? And is the quality of the data enough to allow you to do good geologists?
Yeah, I think so. Let's see. So we will get, from the Curiosity rover, we get hundreds of megabits per day, up to several hundred. With the Spirit and Opportunity rovers, we were restricted to closer to 100, 150 on a really good day, megabits of data. That has accumulated. The Spirit and Opportunity rovers, Spirit was up there for just over 7 years, and Opportunity was driving around for 14 and some, and has been quiet since June, but we're still hoping to hear back. And then Curiosity has been driving around for just over 6 years now as well. And so at this point we have gigabytes worth of data, and we have high resolution imagery. We're able to take images from a camera about 2 meters above the ground, similar to people walking around, but we're also able to take pictures from a camera on the end of the robotic arm, which can get us up close images of the surface with resolutions like 14 microns a pixel. And so we can get very high resolution images of the surface. Now, the catch there is that it's the surface as is. One of the major challenges, I would say, is that we can't cut a thin section, right? But in addition to those images, we're also able to acquire chemical data. So we use 2 spectrometers. One of them is a laser-induced breakdown spectrometer, and this is with the Curiosity rover, the most recent mission. That one will get us chemistry of a spot size about 300 microns across, using a high-powered laser that zaps the rock into a plasma, and then a spectrometer that reads visible near infrared spectroscopy and tells you kind of the composition of that plasma. We have an XRF spectrometer that'll get us the composition of about a penny-sized spot on the surface, which we can brush off. We can brush the dust off of that spot if we have a little brush for that. And then additionally, we can drill into the surface. And then when we drill into the surface, we get a sample that we can do both XRD and obtain the mineralogy. And we have a quadrupole mass spectrometer, so we can actually heat up the sample and measure the volatile elements as they come off up to, I think, about 1300 C.
And so the quantity of the data is among us and is growing exponentially.
Absolutely.
Are you happy with the quality of the data? Is it comparable with what we have on Earth?
Certainly on Earth, we can always take another step, right? If we're interested in something, we can check it again. On Mars, we're always driving, and so it's a lot harder to double check. The quality of the imagery is great. One of the things I mentioned, I would love to be able to cut a thin section. Turns out you don't realize quite how, probably realize they're valuable, but man, to study just a whole sedimentary basin and never be able to cut a thin section, you really recognize the importance of them. The chemical data, though, is good, and when we get mineralogical data, it really helps us understand how weathered these sediments are. One of the challenges that we've run into is that a significant amount of the surface is actually X-ray amorphous, which we were not expecting. So we'll have up to 20 to actually up to 60% amorphous material in these rocks, even though the rocks have been sitting there for about 3.5 billion years. So we would have thought that they had plenty of time to crystallize and reach some kind of an equilibrium state, but instead we'll find disequilibrium chemistry, disequilibrium mineralogy, and a significant amount of amorphous material, which appears to include things like ferrihydrites, which on Earth you can bake at 60 degrees for 20 minutes and they'll be gone. So that's been a challenge with the mineralogy data, but the quality of it is quite, it's quite good. You get to you may not always distinguish between different pyroxenes, but you'll definitely get the quantity of pyroxenes are different,
What about the methodology to acquire? We are geologists, we go to the field and we write down the things, our wish list, and then we decide if we go first to the east, to the west. It depends if it rains, so we do other things. We have priorities. We decide the samples, how to collect them depending on what analysis we're going to do. What about in your case that you have such a large group, interdisciplinary, and they have their own opinions to how to collect the data? How do you decide the methodology to collect data?
Absolutely, it is a challenge. I often show this slide where we've got kind of point A. It's an overhead map of the surface, and we've got point A and point B, and we ask 5 different geologists to draw the best path to get us to point B, or the safest path for the rover, and we have 8 different paths drawn on there. You're definitely compromising with a large team with all a variety of expertises and backgrounds. We work together on daily basis to plan for the next day on Mars. We also plan we plan a day on Mars and we plan one day ahead, and then we also plan with that group what are we doing for the next week, and then we tie that back. So every 6 months we'll all meet in person and discuss what have we seen. Are there any kind of unique observations? We'll constantly be discussing this as well. We have teleconferences multiple times a day, but every 6 months we'll all get together in person and come up with kind of our long-term plan and what kind of things that we will allow ourselves to deviate from that plan for, right? So we'll joke about the gold standard would be dinosaur bone, in which case we would definitely turn the rover around, right? But short of that, what are the things for which you would actually turn the rover around versus kind of make progress and continue towards some of your main objectives for the mission, which may require continuing to drive past observations that folks would really like to make. And so it's definitely a balance. It's a balance on a daily basis, it's a balance on a weekly basis, and it's a balance on an annual basis, to make sure that we're getting enough observations to be able to characterize the places we've been, but also continuing to move and getting to see different parts of the geology on Mars. And one of the other challenges, one of the ways that we discuss, and every now and then we're able to do this, we call it a walkabout, where we try to imitate the approach of terrestrial geologists. A lot of times on Mars, when you're driving on one path, when you encounter something for the first time, you have to decide right then whether you're going to sample there or continue driving, and you may not ever turn around. Every now and then we'll get to a location where we know we're interested in sampling, and we'll do something a little more like what a terrestrial geologist would do, which is to say we'll drive around an area, look at it first, drive around the area maybe again, and get quick samples of the chemistry, like use the laser or use the XRF kind of instrument, get the bulk chemistry of the area, and then select where we're going to drill and get the mineralogy. Other times we really do have to select as we're driving or using orbital data where we think the best spot will be. Sometimes that works, sometimes it doesn't. Recently we've had some major challenges with the drill. We were trying to drill with selecting drill samples, we were trying to drill into this ridge line, and it turned out the ridge line was a ridge because the rocks are very hard. And so the first 3 spots we picked to drill into and sample this particular rock, the drill was not actually able to penetrate into the rock, and so we were not able to sample. And so we've learned more and more after that particular experience how to look for places where, for example, our little brush that we can brush the rock off with actually leaves stripes in the rock, and we're shown visually that the rock is a little bit softer there. And we just were actually successful last week. And so we finally drilled into that rock, and we'll hopefully move on soon.
Once you collect all of this data and you have these observations, when is the right moment to let the others know? At the very beginning, I bet that you have a lot of discussions about what it is, what it's not, some theories more that at some point they start agglutinating together with the observations, and maybe discussions and disagreements. When is the right moment to let the public know what you find, and how do you do it? How do you do these communications?
Yeah, NASA has pretty strict directives on that. And so all of our images are released to the public as fast as we take them. So images are available to the public as fast as we see them. So, for example, in that case, if we take a picture of the drill hole, then everyone knows we've drilled. So the public can keep up, and a lot of people do keep up with all of the things that the rover is doing. We also kind of blog after each day and just discuss some of the process. And so we'll blog and say, today we had a lot of debates, but we decided to take the chemistry and move on, or we decided to drill here for some of these reasons. And so a lot of it is available to the public. Certainly the interpretations do take longer to hammer out. So image data is available immediately. Chemical data that is data. And so you can kind of read off what the chemical elements are, like from the laser and the XRF, is put available to the public after about 3 months for every sample we ever do. When we find something interesting, we try to pull it together into a press release as fast as we can, as soon as we kind of agree on it to some extent. And so we do pretty regular press releases, especially as we're driving. There'll be probably a couple, once or twice a month, we'll do press releases kind of detailing what we're seeing. And then for some of them, like the mineralogy samples or the mass spec, that take a lot more data processing and a lot more arguing about whether or not we are completely sure that this is a pyroxene and this is, the amount of amorphous material. Those will take longer and tend to come out in publications or in abstracts for different, like the Lunar and Planetary Science Conference.
And do you tend to do it more in abstracts or in publications? Because publications of whatever you write, they become historical.
Yes. Yeah. And we do both. Absolutely. So we'll get them out in an abstract or something just to get it out quickly, or to make sure that that data is available. And so we've got people on the team analyzing the data, and we write a lot of publications that are that try to capture what we've done as well as what we've seen, so that they are reference data for the public. And so certainly the pure data products, the immediate data products, are made available to the public, but those references also really help. They'll explain, for example, a lot of times if we do a directed campaign at a certain site, then someone will write a paper kind of stitching together the sedimentology, the stratigraphy, and where we took observations, and do kind of first order interpretations, but there's always a lot of room to follow in behind that and get in some of the details. But those first order papers are really important to the public, and so that's really part of our job as the rover team to share the observations.
So in this special case, where we said that the critical mass, it is not more than few tens or hundreds of people when you talk about geology of Mars. We're talking about publishing data. Do you still think that the classic peer review international journals are the way to go? Or maybe, as you mentioned, the blogs and the press releases, there are maybe a faster way, because after all, there are not many people that they can check on what you do.
Well, because all the data is made public, there tend to be some people checking on everything we do. We still do follow the publication route. I do think it's also important to keep up with the blogs, keep up with some of the other ways that we try to disseminate information through abstracts, especially through blogging, through press releases, making sure that some data is available, or like that data is available immediately. And then also because the actual raw data is made public pretty quickly after it's taken, that data is just making sure we document or comment on that data as we're publishing it. That helps so that it's a little more searchable. And then publications really do help to make sure that you have kind of an organized set. I think publications help us sometimes because as we're writing them, we make sure that we kind of can tell the whole story and keep it together. And that's maybe an advantage to publications above any of those other quick releases, in the peer review and in the team review process. So we'll do science team reviews or double check our findings with the science team in addition to peer review, which also helps make sure that each of these kind of major publications that are telling a story of a different spot that we've seen with the rover, at least, gets the data out there, gets it out in a clear format, gets it out with tables and different things so that folks in the future, we tend to be concerned about people who want to continue to use this data. And so we are trying to get it out in ways that they'll be able to use it.
Very interesting to have that release of data for everybody, not only for the taxpayers that they are financing the missions, but my understanding is that for everybody in the world, right?
China's one of the biggest downloaders of NASA data. Absolutely. So it's all available to everybody in the world.
That is fascinating. As fascinating it is the concept that you just mentioned of writing down black or white and discovering that you don't really know everything and the story doesn't really make completely sense. So until you don't write it down, you don't really know how to explain it very well. I have some questions that I collect from kids.
Okay.
You know that you love to do outreach. And so the typical questions that we adults sometimes we're ashamed of asking. But here we go. So tell us, Kirsten, why Mars is the red planet?
All right. It's red because it has iron oxides, and it has iron oxides that have been blowing around on the planet for about the last 3 billion years. And so they've done a pretty good job of coating the whole planet. About every 10 years in there's a dust storm that kicks a bunch of that dust up into the air. We just had one this year, blocks out the sunlight, spreads that dust all over the planet. And so it's really, the whole planet is covered in rusty, fine dust that's spread around and made the whole planet red.
And when we see the images from NASA, are those colors the colors that human beings would see on Mars?
So it's tricky. We'll actually release a couple of sets of some of the images. A lot of times in our press releases, what we do, and amongst our team, we'll white balance the images. And so when you take a picture on Mars, you're looking at the Martian atmosphere. And so it will appear even more dusty and red and brownish. If you had an Earth-like atmosphere that leads to, the reflections that give us the blue sky, then you would see them with this white balanced flavor. And so a lot of the time, if you ever see a picture of Mars where the sky looks blue, that's a good indication that we've adjusted it so that it's what a human would see if those rocks were on Earth. Because that's the way that, as geologists, we typically understand rocks. If it's really dark, reddish, brownish sky, then that's what you would see still. It's just what you would see if you were on Mars, which isn't what you're used to seeing because it turns out our atmosphere adjusts those colors for us.
All right, here another question from another kid. Is there water on Mars? Was there water on Mars?
Yes, a classic question. We know that there was liquid water on Mars in the past. We know that there is solid water on Mars today. So there is ice.
How do you know that?
We have seen it. The Phoenix lander went up actually to pretty close to the North Pole. It went up to the northern regions of Mars, and actually during its landing process blasted a lot of the dust and dirt off of the rocks and found that there were big areas of ice just centimeters below the dust cover.
Ice of
water ice, H2O, almost pure actually in a couple of places. In addition to that, it has a north and south pole that we can see from orbit. So if you see a picture of Mars, it's got a little white circle at the top. That is mostly water ice. In the winter, it will accumulate some carbon dioxide ice or dry ice, but it is mostly, the bulk of it is water ice.
So there is space for a glacial geologist to study there?
Yeah, absolutely. We've got a lot of radar images over those glaciers that form the North Pole and the South Pole, and there's subterranean glaciers that we've also seen through radar and with that Phoenix lander.
And the ice never melts?
So the atmospheric pressure is so low. The atmospheric pressure is 6 millibars, which is 0.6% of Earth's atmospheric pressure on average. And that is actually so low that liquid water is not stable. So water will only go from the ice phase to the gas phase and will not stay in a liquid phase because there's not enough pressure. If you have certain types of salt, you can make a brine. You can depress the freezing point of water, just like you do in the winter. You put ice on the roads so that the ice doesn't. Sorry, you put salt on the roads so that ice doesn't freeze, so that cars don't slip. Well, if you have certain kinds of salt on Mars, it could actually allow there to be a brine that's formed just around those salt grains. And so we've actually been discussing a lot recently, based on recent observations, whether or not we know actually that there is some of this salt sprinkled all through the soil. And one of the salts that will do this is perchlorate. And we think there are both calcium and magnesium perchlorates sprinkled in fine amounts all around the soil based on atmospheric reactions. So those perchlorate salts could be creating brines if they're concentrated enough. So that's the only chance for having potential liquid on Mars, and it would be closer to wet salt than than real water, maybe.
But still something flowing.
Potentially flowing, yes. And that's kind of the evidence we're looking for. So we've seen what we now think are probably dry grain flows, but they behave a little weirdly, and we're not sure if they become unstable because of some kind of brine forming in some of the craters near the equator in the summer, where we see these dark streaks that move down the craters.
Then you said that there was liquid water in the past.
Absolutely.
How do we know that, and when did it happen?
Yeah. So we know that there are a lot of secondary minerals like clays and salts that form in water. We knew from early on that if you look at Mars' surface, there's a lot of large channels that lead to low areas like craters, or the entire northern hemisphere of Mars is actually low compared to its southern hemisphere. So we've seen these channels. We see some channels that really look like a river network, similar to what you'd see on Earth.
And you see them on the surface?
On the surface
but
today.
They're very old.
They are very old. So a lot of the surface is most of the surface is more than 3 billion years old. So from kind of counting the number of craters that have impacted in some areas since it was formed, then you can kind of get a sense for the age. And that's how we know that a lot of this is more than 3 billion years old. The river channels, we think, the bulk of the water, we think, was active closer to 4 billion years ago, because that's when we see a lot of the most alteration minerals, the most phyllosilicates, the most clays. Over the next kind of era, from about 3.8 billion years to 3 billion years, we see a lot of salt deposits. So it's kind of clays, then salts, than just dry iron oxides.
And the reason why we have such an old sediments or landscapes exposed today is because there is no plate tectonics in Mars?
Exactly. exactly. There are no plate tectonics in Mars. There's actually no plate tectonics the type of plate tectonics that we see on Earth, including subduction, we don't see anywhere else in the solar system. And so Earth is a unique example of plate tectonics. On Mars, instead, the surface slowly dried and got older, and nothing ever shifted around. And so a lot of the...
What do structural geologists would do on Mars?
There actually is still work for structural geologists on Mars. You don't have plate tectonics, so you don't have subduction zones. You do still have tectonic action. So we have, for example, we have the largest volcano in the solar system, Olympus Mons. It's 3 times the height of Mount Everest. And in building up that big of a volcanic edifice, right, you do actually weigh down the lithosphere in that zone, and you'll have a lot of kind of expansion cracks near it and compression cracks on the other side. So we will have fracturing systems, but not subduction, not moving plates.
Well, another question from a kid.
Yeah.
Do these volcanoes explode?
Do the volcanoes explode? Yes, absolutely. There has been volcanic activity on Mars in the past. We think a lot of that peaked again back when a lot of the surface formed closer to 3 to 4 billion years ago. However, there are some lava flows that appear to be geologically young, and that could be hundreds of thousands of years. So in theory, some of the volcanoes on Mars could still be technically active and just dormant. We certainly haven't seen any volcanoes erupting today, but we do see some relatively young flows that could be hundreds of thousands of years old. And really one of the key things that we're going to find out soon is that the InSight mission to Mars is a small lander, and it lands in just a week or two here, actually on the surface of Mars. And that mission's goal is to drill a hole that will be up to 5 meters deep. And in the process of drilling that hole, it's going to pause several times and measure the heat flow out of the interior of Mars. And it will also set down one seismometer. It's sort of limited, but one seismometer and some heat flow measurements can hopefully tell us about how much heat is still escaping from that planet and whether or not there could be a liquid core.
So a seismometer is to measure the earthquakes. Are there earthquakes on Mars?
Well, we call them Marsquakes. But we think that there are. So there are still impactors that hit Mars, and so impact could cause a Marsquake. There are also landslides in some of the steep-walled craters and in the North Pole, especially because of that CO2 and H2O ice kind of freezing and shifting up to the North Pole and then shifting down to the South Pole in the winter. Some of that will cause landslides. And so it could be an impact crater that causes a Marsquake or a landslide that causes a Marsquake.
So landslides and volcanic eruptions, either explosive or not, it seems that there are not so many if they don't clean up the surface completely, right? So it should be something minimal volumetrically at least.
Yeah. These wouldn't be major. If you think about Mars, it is smaller than Earth. But one thing that helps me get a sense for it is if you actually squished all the continents together, Mars and Earth have about the same land area. And so you do have a lot of land. And so, on Earth, we also don't get a volcano that covers the whole thing, thankfully. But any of that activity would really just cover a small fraction of the surface.
Okay. A question from Mysterious Mike, which is working in here. Are there some creatures that are walking there in the red planet? Is there life in Mars? Was there life in Mars?
It's a good question, and it's definitely one we're all very interested in. I don't think that we have extant life walking around on the surface today. If there is life on Mars today, it is microbial and probably not near the surface.
Why not on the surface?
Well, the surface is exposed to a lot of radiation from the sun, and so it's not a very friendly environment for life. A lot of organics break down in that type of radiation. Mars lacks a magnetic field to protect it from the solar wind, and so the surface is really experiencing bombardment of gamma rays and solar radiation.
Before you go deeper into this important but simple question, how do we define life once we decide where we want to look for something in the sky, in this case, life, but life is not right. It should be something that is alive.
Mm-hmm.
It's like saying love, right? You can't go and find love. So how do we define what we're looking for?
Yes, that is a whole question. So certainly the first thing that we do is we think of life as we know it, right? And then we think of kind of key characteristics of life as we know it. And there's some of those that will be incredibly hard to find or characterize. But one of the first things that we did was we sent several missions to Mars with the theme of follow the water. Go find places where water interacted with rocks and just show that that water was friendly. And in fact, the first time that we found sedimentary rocks that had been cemented by groundwater, it looks like the groundwater in that case was pretty acidic, close to battery acid. So that was not looking super friendly for any kind of life that we knew. We do have extremophiles on Earth that can live in things like close to battery acid, but it's probably not the easiest form of life to start. With the Curiosity mission, we found just hundreds of meters of stratigraphy of mudstones that formed in a neutral pH, not even super salty lake. And so we do think now that there were environments on Mars that we would classify as having lots of fresh water, essentially. And then our next challenge was to say, well, was it habitable? And so we defined habitable as a place that had liquid water, had energy sources for life, and those could be chemical energy sources like gradients between reduced and oxidized iron, or things that could power microbes on Earth, gradients between reduced and oxidized sulfur. It had to have all of the elements required for life. We know those as carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. And then that environment had to persist for some period of time. And that's kind of our minimum description of an environment that would be habitable. It's one that has the ingredients, has energy, has water, and persists for some period of time. And so we have found environments like that on Mars now. And so now we're looking for the next step. We're looking for carbon-based molecules that would be indicative of life. And the Curiosity rover that's up there now has found simple carbon-based molecules, although nothing quite like an amino acid, more like benzene or methane, ethane. So simple carbon strings. And it also found refractory carbon or something more like kerogen that was probably delivered by a meteorite. The next mission, Mars Science Laboratory, which will launch in 2020 and land on Mars in 2021, is taking that next step. And the next step is really to bring samples from Mars back to Earth. So first look at them with Raman and see what kind of aromatic, kind of carbon groups we have in those carbon-based molecules. And then bring samples back to Earth, which will take just over a decade and about 3 different missions, and bring those samples back and be able to really investigate what kind of carbon we have in them. And so we're going to look for places that we know are habitable, look for places where biosignatures might have been preserved based on our understanding from terrestrial rocks, and search for those fossils that would start to answer that question of whether life could have been on Mars. It's certainly a tricky question, and one that we have extended discussions about. What is habitability? What is life? And what's your best chance of finding it, especially if it was ancient and maybe only in a few places on Mars?
Is this question an important question? What is the positioning, the priority of the many things that you are looking for in Mars? What is the most important question to ask and to solve?
It's certainly one of our priorities. In terms of our understanding of where we are, I mean, it's just one of the biggest questions humans ask, right? One of the biggest questions we ask as humans is, are we alone in the universe? And Mars is probably our best chance to look at another planetary body that was once in a habitable zone or had liquid water stable on the surface for potentially extended periods of time. By that I mean hundreds of thousands or maybe millions of years, and could have formed life. If we find some kind of microbial life that that evolved on Mars, and when it was only in the habitable zone for maybe a billion years or so, compared to Earth, we'd just have such strong evidence that microbial life can initiate anytime you have the right conditions, and that would tell us in our search for exoplanets and our search for life across the solar system that we're much more likely to find communities of advanced intelligent life like ourselves. Without that first example, it's hard to know what the hardest step in starting life is. So we have our one example on Earth, but the opportunity to investigate Mars, which is, much closer than any of those exoplanets, at only about 8.5 or 9 months journey away for our spacecrafts, we get to ask that question. We get to ask, does life start whenever the conditions are right?
So you said 8 to 9 months to go to Mars?
Mm-hmm.
Okay, we can make it.
Yeah.
So, by the way, the other question of the kids, when are we going on Mars? When are we traveling and landing, if we
Yeah,
are?
well, we've got one on the way right now. We're mostly sending robots. That's the truth. So we've got one on the way right now. We've got one going in 2020 for NASA. So 2 big missions coming up. The 2020 mission is, like I said, the first one that'll actually bring samples back. So the plan for that, let me just get a sense for this. The plan for bringing samples back is for Mars 2020 to drive around and collect the samples. A follow-on mission will come, get the samples from 2020, get that cache of cores. These are just pinky-sized cores. So get that cache of cores, put them into a capsule, launch that capsule into orbit around Mars. A third mission will then come from Earth. It never has to land on Mars, but it will catch the capsule that is orbiting around Mars, bring it back to Earth, and land here, and we'll be able to collect those rocks from Mars and actually analyze them in our laboratories. And so that will take probably about a decade, maybe a little plus or minus several years. And so
Probably plus.
Probably plus. Most likely plus. And so just to keep in mind that that's kind of the level we're at for sending things to and from Mars. Now, I certainly don't want to send a person before I've shown that I can bring some rocks back safely, bring some pinky-sized rocks back safely. So we are a little ways out from actually sending humans there and having that technology ready. One of the things that I think will be a good indicator that we're getting a lot closer is when we either go back to the moon or to an asteroid. It's very difficult to launch from Earth because of our atmosphere and gravity. And so you can't carry as much of the materials that you need for your humans and send them all the way to Mars, even with your heavy lift rockets. So what you can do is you can build a colony basically on the moon, collect a bunch of materials there, send your astronauts there. They'll pull all their materials together. You'll send some materials ahead of them to Mars, but it's also good to go with some of the things that you'll need, right? So the astronauts can have a base on the moon and actually gather their materials and then launch with the people and some of the materials or food that they'll need together from the moon. And that's much easier to get to Mars because you're launching with less resistance from gravity and atmosphere. And so that's a good step. So watch for when we really start sending people back to the moon or sending people back to an asteroid that's closer, because that'll be the first step in really sending them to Mars.
Do you see any competition from different groups or different countries for the study of Mars and the benefits of studying the planet?
We are really excited that there are so many other groups right now that are really starting to be interested in Mars. And so in 2020, because of Mars and Earth's orbits, there's only a chance to launch to Mars every 2 years. So 2020 is one of these launch windows. And in 2020, the European Space Agency is sending a rover. NASA is sending that rover that is currently just called the 2020 rover. The United Arab Emirates is sending an orbiting mission. SpaceX is planning to send some capsules, and I believe China is sending an orbiter. And so we are getting a lot more interest in going to Mars based on that 1 year opening, or that one opening for a few weeks, and having 5 different groups planning to send missions to Mars. And
so what are the implications of this kind of race?
Oh, I think it's exciting. I mean, we're always hoping that people really truly are inspired by this, and see how it can both inspire people and inspire different kinds of research and inspire just different kinds of understanding. And so this is a strong indication that there are a lot of people more interested in that. If we send people, it will be a multinational effort. It is necessarily, I mean, that would be one of the greatest achievements of mankind, and it will not be the achievement of only one nation. And so really having that many countries, that many companies, that many people really excited about Mars exploration means we are getting closer to being able to think about and achieve some of those really big goals.
In your personal opinion, do you think that all of these countries or entities, public or commercial, are they moved by the same goal, or they have completely different goals?
I think sometimes we have different goals, but a lot of those goals, I would say that in the team for the Mars Science Laboratory, we have all different goals. I would say with 400 scientists, you have at least 400, probably 800 goals, right? I mean, I think that we're all thinking about this in slightly different ways and come from different approaches, and a lot of it is working together to compromise and find ways to achieve, as many of those goals as we can with each mission, and really maximize the return to the public, maximize the return to humanity. And the way that you do that is by having people with different goals and different objectives, and showing that you can work together to achieve the most important of all of them.
Thank you so much for all of this information that you are giving us. I'm here shooting at you question after question with the excuse of the kids, of those simple questions that we all should know and keep pace on the information that is coming from Mars. I really appreciate that, and I know that you have your heart on the outreach, and that you do a lot of volunteering also. So do you want to talk about that and the importance for geologists in general, not just Mars geologists, which are shining because of the object that they are studying, the importance of spreading out the word and reaching out and communicating better to the society at large?
Yeah, absolutely. I mean, especially with Mars, but also with, Earth science, or with any science that we're doing, I do think part of our responsibility, especially when we're funded by the public or we're funded by people, is that our responsibility is to give back and share the information that we're seeing. I think that we'd be surprised at how much people do understand and want to learn, and I mean, I see that every time when even young children come up with clever questions about Mars and think about, or the world around them, and think about like the landscapes that they've seen. I think we have a responsibility. We also have a privilege in getting this chance to research new things, to explore in Mars or explore on Earth. And that privilege to explore can be matched by our communication and our willingness to share that with more people. I think for me personally, it's been a huge inspiration to my own research, and being able to learn to answer the questions, learning to first off communicate to all sorts of groups, and especially school kids. They will always tell you what they're thinking, and if you're boring, then they'll let you know. So they're a good group for me to have learned to frame my research, to frame my stories, to understand more deeply and more thoroughly, and then find ways to communicate it in a somewhat more entertaining way. And so it's actually benefited me greatly to have reached out to so many school groups and teachers and people with basic questions that come from different perspectives that actually may not be that basic when we think about them geologically. Let's see. I guess it's been inspirational for me. I always encourage students in particular to learn to communicate by talking to kids who will, like I say, give you that feedback. And then I think we do a better job of communicating also with our own colleagues and communicating our science in general. And science really is about communication, because we're not actually making progress if we're not able to share what we've done. We're not, as a community, going to progress unless we know how the community has already made a lot of findings and what the community understands. It's all about communication. So
I hope one day you'll write a book or an ebook about it, or because certainly every single second of your experience as a geologist of Mars is a piece of history. And especially because you said you start the studies a long time ago, so when very few geologists were around.
yeah.
So thank you so much to Kirsten Siebach, professor at Rice University, Department of Earth and Environmental and Planetary Science. This is Mini Geology. This is Daniel Minizini, your inquisitive geologist at KPFT Houston, HD2 channel. And if you want to listen to this interview again, you can go to minigeology.com. You can write me, or if you want to ask questions to Kirsten, you can still write to minigeology@gmail.com. Or you can also Google Mini Geology at Rice University. You'll see we have kind of a brotherhood in there, and there are some web pages where you can see what is this project about, where we try to spread out the word of geology and let you understand a little bit better the beauty of our beloved discipline. Thank you very much to everybody, and that's all for today. Thank you, Kirsten.
Thank you.